Ja, ja. Jetzt. So, meine Güte. Das ist immer schwierig. Aber gut. So, everyone ready? Okay, good morning, everyone. So we can continue with our lecture about energy storage, in this case about biomass conversion. And I have to say a little bit about the biomass conversion, how we can come to carbon monoxide and hydrogen, but we will do that a bit later. So you should just have it in mind that there will be also an information how you can transform the biomass into the starting compounds for the Fischer-Tropsch synthesis. That's where we stopped last week, if I remember correctly. And that means that we have discussed a little bit about what you can get if you have different chain probabilities alpha for the growth of the hydrocarbon chain. And so that's just to say that you always get a mixture and that you just have to go up from 0 to 100% and then see, okay, you have for 85% probability for the chain growth, you have maybe about 20% of excess and then same amount of diesel, a little bit more on gasoline and so on. And what I have to tell you a little bit is about fossil fuels. You know that probably, but we're speaking here about diesel and we're speaking about gasoline. Do you know the difference between the both mixtures from the chemical composition? Probably not. Okay. But I guess you should know it at least a little bit. And therefore, I have also 2 or 3 slides here about that. If we discuss about gasoline, we have to consider what is in there. That's always, if you go to the gas station and you fuel your car, you will always get a mixture of different compounds. That's not one single chemical compound, that's always a mixture. And therefore, the company selling this gasoline has to test somehow how this composition work with your motor. And for that, they have defined, or there was defined, the so-called octane number. And octane number just means that we have a system, a test system, which just says, okay, if we have this composition of the gasoline, we will end up with about with some properties. And the test system is that you have either an N-heptane, which is just a hydrocarbon chain of 7 carbon atoms. You can know that from alkane. Heptane is just the alkane with the carbon number 7. And then you also know 2N plus 2 is the number of the hydrogen atoms there. So that's C7H16. And the other component of this mixture is isooctane. An isooctane you see there, that's not longer one straight chain. It's a so-called branched molecule. So you have 1, 2, 3, 4, 5 carbon atoms in a line, and then you have some side groups. And so this is to make it completely, because that's always methyl groups which are at the side there. That's at the 2 position. You have 2 other groups, so methyl groups, which is just a CH3 group here at the end. So it's a 2,2 methyl. And then we have to go on. 3, 4. It's not so nice. How can I go? Huh? Okay, there we have to go. Okay. But that's not so nice. So we have 4 methyl. That's only 1 methyl group which is there. And then we have to give the name for the longest group here, and that's the 5, as I said. And so that's a pentane. Maybe I'm writing this here. So in total, it's a 2,2-dimethyl 4. Easily, it's called isooctane. And these 2 components act quite differently in the motor. If you have a motor for gasoline, that will be much better working with this compound than with that one. And so we have to look at if you go for the gas station and fuel your car, there will always be an information about the so-called octane number. And this octane number for super, which you can get here in Germany, is about 95. But you can either get these 95 for a mixture which is just consisting of these 2 components, and it's 95% of isooctane and 5% of heptane, then you would have 95 as an octane number. But you can get these octane numbers also with some other additives. And so we here have a list of just about the octane numbers, which is depending on the length of the chain, the carbon chain, and it's about the different compositions which you might have, or the different branching side groups you have, and then there are different numbers. You can also have some aromatics. We have discussed about benzene molecule last week. So you can also use that. 99 would be the octane number. So if you have pure benzene, you would also, that can also work with your motor, but it's a toxic compound, and therefore it's not so good to fuel your motor with that. And you can have maybe also some oxygenates, which are alcohols, for example. You can have methanol and ethanol. They're also above 100, so they're even better than the isooctane with that respect. And so the oil companies just mix different components together. And then they only have to make sure that they always have octane numbers of 95 or higher. What you can learn for gasoline is that these branched molecules have always the higher octane numbers. You see, if it is 1 time branched, it's less than if it is 2 time branched for this C7, for example. And that means the more branching you have, the more side groups you have, the better it is for the gasoline. that's important because for the diesel, it's the other way around. And therefore, you are also strictly asked not to fuel a diesel motor with gasoline and vice versa, because then your motor will break, and so that's not helpful. And so we have another system for the testing of the diesel. It's a so-called cetane number, and cetane is coming from n-hexadecane, and hexadecane means just 16, so it's in this case C16H2N plus 2, so it's 34. So really a long hydrocarbon chain with 16 carbon atoms, and that's what will give 100% of the cetane, and so it's a straight molecule, a long line, and this is working best for diesel then. And the reason is that if you have an octane number or a high octane number, you have a mixture of these hydrocarbons which is relatively slowly burning. And you always have to ignite it. And therefore, in a car working with gasoline, there's always an ignition needed, which you have in a different step. And so you ignite this mixture, and then it's burning quite slowly. For the diesel, it's the opposite, because that's the so-called self-ignition, which happens in the diesel motor. So you just compress the mixture of the fuel, and then it's self-igniting, so you get this ignition automatically, so to say. And that's leading to a fast burning, and therefore you need another just the reason for that. And so you can then differentiate between the cetane and this octane number, and you have to see that also if you make, for example, diesel or gasoline from biomass, it's of course the same as if you like to do it from crude oil. You always have to consider this. That's just an information for that. So we also go further with our components of biomass. And that means we also have to consider something else than just only cellulose. If you remember last week, we had cellulose molecules, which are a long chain of sugar molecules added together. And now we're going to something which is different. And these are, for example, fatty acids. You can find fatty acids either, for example, in meat, or you can also have some olive oil, for example, and you get then also fatty acids. If you just look on these molecules, you see you have a quite long hydrocarbon chain, and you have another group, which is the acid group in this case, which is this COOH group. And therefore, it's an acid. So this group is always that what you have if you have an organic acid. So we can also remind us for that. And then you have two different situations in these different oils, or different fatty acids, so to say, sorry. They are either saturated or non-saturated. What does this mean? If you have a saturated one, you have a hydrocarbon chain, which is consisting all of single bonds. You have, so to say, a pure alkane. If you go for the non-saturated or unsaturated fatty acids, you always have double bonds with that. And double bonds means that there are carbon or two carbon atoms bond by 4 electrons, so to say. And that means you have less hydrogen on such a double bond. If you have a double bond, maybe I can show that, you have this situation, then you have maybe another carbon here and another carbon there. And that means you only have, since all the carbon, you know that is only 4 binding, you have only place for 1 hydrogen at each carbon. If you have a saturated one, you know that in such a chain you have always 2 places for hydrogen. And then you can have the situation that here at this double bond, you have also a different configuration. Because I can show that in that way, what I just have drawn there, or I can also, and these are also 2 different configurations you have, which are also leading to 2 different effects or 2 different properties, so to say. Because the position of the hydrogens, which you have then here, so either this and this, or that and that, is with respect to the double bond different. You have either you have a planar structure on the double bond, that's always the case. So this is always a planar configuration. So really, as it is shown here in this plane, not longer the tetrahedron angles, which we have if we have only single bonds. So this is this planar, and you have, for this either you have the 2 hydrogens on one side of the carbon-carbon bond, so in this case on the upper side, and this is the so-called syn configuration. And the other one, you have it, the other one of this on the upper side, and the other one is on the lower side. And this is the so-called anti-configuration. And so this is also something to consider for such double bonds. And then what you also have to, what you also can say is, okay, if you have this configuration, you can, for example, have such a situation like this one. And then it is, in this case, like here, or in the going to the lower part, so that's a syn configuration. But it has also another effect, because syn, if you have these double bonds, and it's a bit different at this configuration, you have a situation, if you have more of them, you cannot stack them so well. So you have a more disordered structure here than you have if you have only this this straight and fully saturated alkyl chains, because you have something like a crystallinity which you form on that point, because all these hydrocarbon chains here, they are interacting with each other, and so you have something which you can call, or which is called the so-called van der Waals interaction. And this leads to some order. And this order can be something like a crystallinity. And for that, you have in the whole package, you have a different structure if you have this configuration or if you have this one. And that's also the reason that our body is then interacting differently with these fatty acids. And so it's said that this configuration is more healthy for us than the one which we have there. So to eat such vegetable oils is more healthy than eating meat. Maybe not the one what everyone likes to hear, but that's at least the biochemical background for that. For us, that means we only have to look how that looks like, because there's another aspect which we have to discuss shortly. And this is the aspect of polarity. If you have just a hydrogen and carbon in such a bond or in such a system, you have a so-called non-polar structure. This depends on electronegativity, but for carbon and for hydrogen, this electronegativity is almost the same, and so you have a non-polar system. On the other hand, this COOH group, which is, by the way, looking like that. You have a more polar structure. And this depends on the oxygen, which is also there. And I could tell you a little bit more about that, but we should not do that. But you maybe can also look in the internet or in a book what that really means. And you have this polar group and you have the non-polar group. And that's something we have to keep in mind for a moment, because that's really what is characteristic then for such a fatty acid. And so there are different of these fatty acids. I guess there should be some summary on the next slide. You see that you have saturated fatty acids, you have mono unsaturated with one double bond. You can also have polyunsaturated fatty acids. There are, for example, 2 double bonds, then in that what also you can see. And if you maybe look for the names here, maybe you have already heard some of them. But the characteristic is you always have this COOH group, and you have this long hydrocarbon chain with the different double bonds. So, and this compound or these molecules we can also get from biomass. And that's what we have to look on a little bit more, because you can, or nature, our body, so to say, if you take up some of these fatty acids, you will not do that for just the fatty acid alone, but you always will have such a system where you have the so-called triglycerides. So 3 fatty acid molecules are connected together. And the connection is done by such a bonding. Now I have to go by this kind of groups. And these are so-called ester groups. And these ester groups you can hydrolyze, so you can just split them by using water. And then you get an alcohol where you have these characteristic OH groups, which we also have seen in the sugar molecules. And you have the 3 separated fatty acids. And this 3 separated fatty acids means that they now are not longer connected. And of course, they could be different because now maybe not on this figure. Here they are all the same because you always have the same hydrocarbon chain, but you can, of course, also have different chains there. And this hydrolysis is something which you can also do the other way. So you can also put an alcohol and a fatty acid together and form an ester from that. So that's a reverse reaction which you can have there. And therefore, there will also be an equilibrium, but it doesn't matter. But you can say, okay, we can do it this way, and we cannot also do it that way. And that's important then for the biomass. So coming to that means that we have a possibility to form, and the question is, why is it diesel and why is it not biogasoline? I guess that's something you should know already. Because what was the characteristic of a diesel in contrast? You have long hydrocarbon chains. And these hydrocarbon chains, which are in these molecules which you have in fatty acids, they are also always, we have seen that here, you have carbon numbers from 12 to 18 here, so that's always long hydrocarbon chains and not branched, just one line. And that means this is going to diesel. And what is done there is you get the oil crops, you have the seeds from that, you have to extract from the seeds. Then you have to clean it a little bit. That's what about refining. And then we have this to do that, what is here called the trans-esterification. And the trans-esterification means that we have to hydrolyze original ester, this triglyceride, where we have this 3 fatty acids bond together via this alcohol glycerol, which you have seen on the slide before. Maybe I'll go back to that. This is the glycerol, which you then get from the hydrolysis. And that's also said here again. But now we want to have, for the diesel fuel, we want to have the single fatty acids. And then we are just reacting that with a different alcohol. And for example, this can be that one, and that one would be easily methanol. We have these CH3 group, which is the methyl group, and then you have an alcohol group, and therefore the name is methanol, and we will talk about methanol also another way. So, and then you have destroyed this structure with in the triglyceride with the 3 ester groups, and you have always only one ester group with the methyl then at the end of the process. And this is what is the trans-esterification. You get the biodiesel and you can drive vehicles with that. And then, of course, if you do that and if you burn these hydrocarbons, you also get carbon dioxide from that. So like you do it if you have diesel, which is from raw oil made from fossil fuel. But in this case, this carbon dioxide has reacted before, or will maybe also next time react again in the photosynthesis, which we discussed last week, and then growing the plants again. And so it's a recycling so to say, of the carbon dioxide. And so that's if you can do all these steps, and that's of course the problem. If you would do that all with 100% efficiency, you will have a fully recycling. Problem is that with all these steps, for example, also the trans-esterification, you will never have 100% efficiency. You will always have maybe 90% or so, and so you always lose a little bit in the steps.
And you also need energy to get to the refining.
For sure.
That also takes.
But if you use crude oil, you have to do the same steps, because you also have to refine the crude oil, and so this energy step is also.
I'm not saying that.
No, I know what you say. That's true. But so to say, all the processing of the crude oil will just need about the same amount of energy as for this process. That's what my statement is to that.
Okay.
But you are fully right. There is a need of energy, and you also have to make sure to make that as efficient as possible. But it's a way to get biodiesel, at least in Germany, but also in other parts of the world, I guess. A route which is maybe not so much done for such buses, but also it's done for that. But if you go in the field of agriculture and have some machines which are also running with diesel, in this area, they will always be using or trying to use also biodiesel nowadays.
So is it profitable? Like, we know we get biodiesel and it's good for the environment because it is circular.
Mm-hmm.
Is it profitable like at the moment?
Now, the point is whether it is profitable or not depends how easily you get the sources. Because if you, for example, you have always your fields, and you have also some place for maybe also growing some sunflowers or something else, which gives you the seeds. Then for people in agriculture, it's maybe they just have it in place, so to say, and then they can also do that. Depends of course a little bit how big the amount of seeds from the different sorts is what you have. But the good point is, I don't have the slide with me, but you can do that in a very easy process. So in principle, you can also do all these process of extraction, refining also with materials which you can, for example, have in your garage for the car. So that you just can do that quite easy. You don't need a big industry for that. Yeah, that's a little bit answering your question. Okay. So there is a possibility to do that, and it's also done. That's what we can also say. Okay, we don't need that anymore. So I have to go to the next one. And now the question is again how to go there. If I want to have the next presentation, I have to go for that. So this is the wrong one, but that's not any problem. So now we have to go back for the full screen. Okay. So that formation of biodiesel is one way. But you have other ways, and we discussed a little bit about not all these components here, but the main ones. And we see that we can always get a circle from that if we can use the carbon dioxide or if we do that with biomass, the carbon dioxide, which we have as an exhaust gas from all the motors, for example, we can do photosynthesis with that, or nature is doing photosynthesis with that, and then you're getting biomass again. And you have the seed oil, that's what we just discussed before, but we have today. So that's the oil part, but we also have, for example, the cellulose part and hemicellulose part, which we discussed last week. So we have then carbohydrates from that. So the other one is, of course, glycerol and fatty acids, what we just saw. And so we can then use that in different operations. And so we are getting, for example, fuels, but you can also, with these components, you can make chemicals, you can make plastics. Of course, you can just burn that. Then you get heat. And you can, of course, get also food of that, which is the original sense of using biomass. But we see the other ways are also becoming more important. So and now we have to look for other ways how to do that. And unfortunately, the most important letter is not C. You can also do fermentation. Maybe it's again. So we have a fermentation which is comparable to that what we all do in our bodies if we respirate. So we also have a conversion that we, for example, split sugar molecules and coming to pyruvate and then to lactate, and we get energy from that. Because in all these steps, you have an energy transfer, which is about, or which is working in the sense that we have these molecules, this NAD+, which can go to NADH by this lower reaction. And that with that, you've transferred from lower amount of energy on this side to a higher amount of energy on that side. And then you have this reaction there, and you have also this ADP to ATP, and I mentioned that last week already, that in this ADP you have 2 phosphate groups, in the ATP you have 3 phosphate groups connected to each other. That's more or less the important thing for that. And what one can do, or what can be done by microorganisms in this fermentation steps is to split the glucose molecules, the sugar molecules, from 6 carbon molecules, 6 carbon atoms in the molecules, what we have seen last week, to 2 molecules only having 3 carbons. And that's the pyruvate. And here you see how this is looking like. And what you also see now is that you have some groups which you already know. You have acid group, which we just saw before. And you have another group, this is the CO group, which is the keto group, which we mentioned also last week when we discussed about sugars. So, and then there's a transformation of that because there's a splitting of carbon dioxide. So you remove parts of the acid group. Only the hydrogen is surviving on that. And you see, if you have the 3H3 group and then the carbon oxygen double bond, and then you have only the hydrogen instead of the acid group. And that's what we then have as an aldehyde group. In this case, it's an acetaldehyde, but the aldehyde group is the one which you have here. So this is the first step of transformation in this formation of ethanol, for example. And then you have a reduction of the aldehyde to the ethanol. So there's always, again, the reaction with electrons, because if you have a movement of electrons, you see that here, you have either an oxidation process if you add electrons, or you have a reduction process if you remove electrons. And so that's, for example, working in this NAD plus or NADH to NAD plus. And let's see, this way it is starting here from the right, going to the left side. So you get some electrons out of that. And so you have, in this case, a reduction step, which you have here for this formation of an alcohol from an aldehyde. And also the one before here, it's in principle also a reduction step. If you go from an acid to an aldehyde, that would be the same, but not really, because in this case you really remove carbon dioxide. So that's better to leave it in that place. So you see, electron balancing between different molecules is then leading to some action. And that's what in a fermentation step is done. What we do in our muscles, sometimes if you make sport, for example, you get the same process, having glucose transferred to pyruvate or pyruvic acid, and then you maybe transform it in your muscles to lactic acid. And that's the case if after the sport, some of the muscles hurt a little bit. That's the formation of the lactic acid. And so you have this side, but many microorganisms can do it in this way. And so you have also the possibility to make ethanol of that. And ethanol is a quite interesting alcohol. You can also burn that, of course. So you can use it as a fuel. And at least in Germany, you know that if you go for to the gas station, and then you have this different possibilities of fueling either super or what's the other name now? Okay, forgot it. So, but you see that you have this in the fuel which you have here at the gas station. You can either have up to 5% ethanol. That's the normal super, and then you have also up to 10% of ethanol, and that's also that means that you can also burn that and can use it as a fuel. So, but to be a little bit more generalized with that, you have to have different organisms, and then these different organisms, microorganisms, bacteria, yeast, or something like that, can form different components. You see the lactic acid, you see the ethanol again, you have acetone or some other longer alcohol. You can have an acid, again, acetic acid, for example. And that's all depending on different microorganisms. So the question is, what microorganism should act or should consume the pyruvic acid, and then forming different products from that. And you know that from your daily life, probably that, for example, either if you want to eat cheese and have the the formation of cheese, there are other organisms involved and also other compounds, which are chemical compounds which are formed. But you can also have, for example, wine and beer, and you have this alcohol formation also by a fermentation process. That's all going more or less the same direction. So we see we have already a chance to have biodiesel, so these fatty acid molecules. We have also a chance to have bioethanol, and we will also look in a moment for biogas. This is a little bit the process again for leading to ethanol. I guess you just should have a look on it. You don't have to remind every step of that, but that's more or less that what we already discussed on the slides before. So that's just for your information. Here is maybe that's important. On this slide, all the others are more or less the same. That's what I mentioned before, that we have these ATP and then going to ADP, which is just what is happening in biochemistry and so also in our body for transferring energy. So what you just do is, or what nature is doing is just splitting or adding such a phosphate group. So in the ADP, there are only 2 of them. In the ATP, there are 3 of them. And so you just have a connection of a breaking or a connection of this phosphorus-oxygen phosphate bond. And that's helping to get energy because you see it down here. If you have an ATP forming an ADP from that, you will gain an energy amount about 7 kilocalorie per mole. So it's a kilojoule factor 4.2. It's almost 30 kilojoule per mole what you can get for that. And that's what we saw on the slides before. Maybe go back to that one. Here where we see, okay, there's this source of ADP and ATP. So that's just to provide energy at the right place where it is needed for the necessary chemical processes. So, and then you can do fermentation. And you do that with quite simple reactors. Here you see a line of that. And then you see also a sketch of it. It's more or less a tank reactor. That's also the name, how it is called. And then you have a tank reactor which is stir. You have the possibility to heat or cool it from the outside. You have, of course, to measure the temperature. And you can put in some microorganisms and, of course, also the nutrients, so the biomass. You can have processes where fermentation works with air. There are also some processes where fermentation works without air or on the exclusion of air. So the point is there are 2 different names for that. Either aerobic, so we have it with air, and the main important component with that is oxygen, O2, or you have it in an anaerobic sense. So in this case, you exclude air, or more strictly said, you exclude oxygen. What is the reason for that? Seen that oxidation reactions play a big role in that, all these steps. And so we can, of course, say if we have reactions to do where we want to avoid oxidation processes, we should exclude the oxygen, because otherwise we will have a great chance that there will some oxidation also happening. So that's fermentation in principle. So quite easy process. And with that, and with such kind of reactors, you can then do these different steps, what we have seen before for formation of cheese or formation of wine and beer also. Always looking a little bit different, but in principle, it's all possible in such reactors. So, and then we have to go for biogas. Biogas is the last part, which we do not have mentioned up to now. And so we will have a look on that. And biogas is, in principle, nothing different than that what our cows, for example, if they just eating grass, which is cellulose, so this line of sugar molecules, they just split this cellulose in single sugar molecules. That's the hydrolysis step. And then they do the same steps as we have learned before. They first cut the C6 sugar molecule into two units, so to say the pyruvate, and then they convert it a little bit further. And so they have different hydrolysis steps, and then at the end, there's a step where methane is formed. And this is what you can see around Olden quite a lot, that you have some companies working on the field of biogas formation. We'll go to the biogas again a little bit more, and but if you have this biogas, it's, as I said, methane. So we have, in principle, the methane formation, and methane, you remember that, is just CH4. But methane is also the compound which you have to more than 95% in natural gas. So the fossil gas called natural gas is chemically the same as the biogas you get from this fermentation process. And historically, it's also the same because all this natural gas was produced by microorganisms thousands and millions of years ago by the same processes which are now done in this biogas formation. Yeah, of course, pressure and temperature effects, which may alter this a little bit, but in principle, it's the same. So we have the biogas, and then you can convert the biogas either in electricity or in heat or in both of that. Or mainly it's both of that. And this is something which you, of course, also know from other, I guess, from other courses. So, biogas, how to form that? That we have to look here. It's not a scheme, it's just some sentences written there. You have to do at first a hydrolysis, and these large polymers which you have to split there or which are broken down, as it is said, these are the cellulose chains, where you have these many sugar molecules. And then you do that by so-called enzymes. Maybe I should say a sentence to enzymes. These are biocatalysts. And so that's natural catalysts, which are working in our body, but also on many other places. They are quite different, or there are many different enzymes possible, but the point is they are all very selective. So they just do the reaction which they should do and nothing else. And that's very, very important and very helpful, and we will come to that also again a little bit later. And then we have the splitted sugar molecules, maybe a little bit further. And then they are oxidized somehow to fatty acids. They are forming carbon dioxide. That are oxidation processes. But if you have the oxidation processes, you will also have reduction processes. So as I said, transfer of electrons, either in one direction or the other one. And so there's also hydrogen which is formed. And these are the first components to form. Then you have maybe the formation of acetate, which is more or less acetic acid. So this acetate is, if it is the anion, it's this one. But you can also have a hydrogen atom there, and then it's acetic acid. And this is, if you just look on this molecule, or this ion in this case, but we can also look on the molecule, you will see that, of course, it might be quite easy to form. So maybe this is, I'm just going for that. So that's the acetate, and this is the acetic acid, which is just the difference that you have added H plus, a proton, to that, which is always the case. If you have an acid, you remove the hydrogen or the H plus, and then you get to the anion of that, which is then the one with just the minus. But if you look on the acetic acid, you will quite easily see that, for example, the transfer, so rein formally, of this hydrogen to the first carbon atom, and you then look what you have left for that, or from that, you see that you here have a CO2 molecule, and if you have this one together with the hydrogen, you have a CH4. So you get a methane and you get a carbon dioxide. And this is just what is then happening in the last step, again done by some other microorganisms. So you have the three different steps here: the hydrolysis, the acidogenesis, the acetogenesis, and the methanogenesis. And they are all done by different microorganisms. So that's a lot of biochemistry involved that, which is not so important for us, but we know there are microorganisms doing that. And then we are getting, as said, methane and carbon dioxide. And if you look on this graph here, that's not really one-to-one. It's always a bit more of methane which is formed, but you have about 60% methane and 40% carbon dioxide. So, and then you can do the reactions what we had seen before, because you can, in such a gas engine, you can burn the methane. That's the same what you maybe do at home if you heat your flat. Because in Oldenburg, at least nowadays still, most of the houses are heated by gas, by natural gas. And that's methane, that we said before. So there you also have a gas engine, typically in the cellar or in the basement of the house. And then you get heat of that. But you can also, and you know that from other courses, that you can also get electricity from that. And so this is the way where you have electricity and heat. And that you can do already with this mixture, because the carbon dioxide has no effect. The carbon dioxide is not reacting, because if you oxidize something in this step, the carbon dioxide is already fully oxidized, so nothing will happen with that. But you can oxidize the carbon in the methane to carbon dioxide, and the hydrogen in the methane you can oxidize to water. So that gains the energy which you have either in electricity or in the heat afterwards. What you can also do is to purify this mixture, because you have still 40% of carbon dioxide, which you in principle not use at that step. And so there are also possibilities to purify that all, and then removing the carbon dioxide and coming to values of about 90% of methane. Maybe also some longer hydrocarbons, which are also then formed with that. And so we have to look a little bit on this, how this is done, but we will do that in a moment. That's just to see how such a biogas reactor is looking like if you see it somewhere around Oldenburg. Probably you only see this part. So the upper part, and there might be something in the ground. It depends a little bit on the reactor, which or the fermenter. So not too much to say. Here again, this biogas system. You have the crops. You have maybe also some manure from the animals. You have the bio-waste, which you have from your homes. And then all this can in principle be converted to methane. Also with different efficiencies. The energy crops here, they have always the highest efficiency. So that's again a question of efficiency then with that, which makes it a little bit more profitable than also for doing that. And that's the reason that you have around Oldenburg also a lot of maize, which is grown, because that's the most effective energy crop for the formation of biogas. But the other ones are also good, or they can be used, but with less efficiency. But in principle, that's more attractive to have some waste biomasses converted than something which you have to grow just for this purpose to form biogas. So, and then, as I said before, you have this gas motor and a generator forming electricity and having the heat, which you can either send to the houses around, or you can use a part of that, or you have to use a part of that also for the reactions itself. Because microorganisms always want to have a temperature which is almost the same as we also have in our body. So we have typically temperatures of around, it was set on one of the other slides, of around 35 to 40%, where the microorganisms work best. So, and then you have the possibility to make the gas treatment. so the gas cleaning, so to say, and then going for maybe the natural gas network. So you can, if you heat at home with natural gas or with gas, so with methane, there might be also a chance that you have in this methane also a little bit of biomethane. Chemically, that's the same, as I said, but it can have maybe some different origins. So, how to do that? How to purify that? That's what you see on this slide in principle. So we have this purifying process, which we have to look on, and then we will do on the next slide. That's unfortunately one which is in German, but the main important things are also said in English. So you have a so-called amine scrubbing. And this amine scrubbing is just something where you react carbon dioxide with. And you see you have again a quite long hydrocarbon chain, and then you have a functional group. In this case, the amine group, it's an N nitrogen and 2 hydrogens, NH2. And on this, you can bind the carbon dioxide, and then you get this, which is called a carbamate group. And the nice thing with that is that you can find quite easily this carbon dioxide to the amine group, but you can also remove that relatively easy later on. So that's a compound which is just used to transport the carbon dioxide to another place. Question is what to do then with the carbon dioxide, but there are different possibilities. And so this triangle here, that just means you have to bring energy to that system, to this carbamate, and then you can remove the carbon dioxide again. So typically, this triangle is standing for heat. But heat, in this case, just means energy. Where can you use carbon dioxide for? Have you an idea for that? Exactly. This, what is in here, that's where you can have carbon dioxide, or where we use carbon dioxide for. One possibility, of course, in chemical industry, there are a lot of people thinking on other ways to use carbon dioxide, because in total, we have too much carbon dioxide. So we should find other ways to use that. But you can also press it to the ground. That's another idea, which is also used for the carbon dioxide, or thought for the carbon dioxide. So there might be a possibility to also use that. And I don't know whether I have this figure. No, I don't think so. Okay, so we know.
I also heard that sometimes now they combine carbon dioxide with green hydrogen.
That's something we also will learn about later on, not today. But you have, but I guess there was a free side. So if you just say it, no, that's wrong, of course. So we have carbon dioxide. And then we have hydrogen. And from that, you can, for example, form methanol. Point is that this is not working one-to-one, as you see, because you have 2 oxygens there and only 1 oxygen there. So you have also to consider that there might be another oxygen formation. But in principle, you can, if you have two hydrogens, you can also have a half of an oxygen molecule also there. So there is a reaction forming the methanol from that. That's also something what is done. But the point is also the efficiency is quite good, but nevertheless, it's a relatively expensive way to get also the methanol. But something what can be done. Okay, but we will do it, discuss a little bit about that also later. So what we heard is we have fermentation. We get, for example, also ethanol for that. And the last slides here on this presentation will deal with what can we do with ethanol or what is done with ethanol. We have this fermentation process. We have the hydrolysis before. You have the maybe extraction from sugarcane. So you can have it from corn. You can get it from sugarcane. You can get it from different other biomasses. And you have, of course, to purify it. And purification is something which we will not discuss too much in this lecture, but something what you have to consider. And the main point there is distillation. And the distillation is what, in the case of alcohol, you might know already, because that's what all kind of alcohol or ethanol for wine, for beer, for something else is more or less involved. At least if you go to whiskey or gin or something like that, then you always have distillation processes with that. And distillation means you have a separation of chemicals. So of, for example, an alcohol molecule, an ethanol molecule from water by the use of different boiling points. So that means if you do the distillation, you have to heat up the mixture, and then the alcohol, the ethanol molecule, will boil at 78 degrees centigrade, and it will go to the gas phase, and you can then also condense it again to get the liquid by cooling. And the water will only boil, as you know, at 100 degrees centigrade if you do it under normal pressure. And so you have a separation, and you can do that in a continuous way. And this is done in large apparatus then in industry at many places. So that's something very easy to get then pure ethanol of that. That is not so easy, you see in this scheme, because that's a way to come from a quite viscous liquid from sugarcane. That's what you see here at the right upper part. That's a brownish, quite viscous molasse. And from that, there is, of course, a process to make ethanol. That's a process mainly done on all places more in the south of the world, where you have a lot of sugarcane planting. So maybe in your home countries there is much more of that than it is here in Germany. But there are also these ways to get then at the end, if you do it the whole process of 100% of ethanol. And what you see here is you have to clean the molasse a little bit. You have to bring the, in this case, microorganisms, in this case it's yeast, to that. You have to make sure that everything is sterile. So you have that the microorganisms can really live in a proper way. And then you have this fermentation tank. That's all at the beginning of the step or the process. And here, in this fermentation, as we have seen before, you form the ethanol. And then all what you see on the right side here, it's all cleaning. So it's all removing chemicals which you not want to have in the final product, but which are also as side products formed in the fermentation process. Also, these microorganisms are not so 100% selective in their work. So you have to clean it, and then you have these different separation columns to get rid of the aldehydes, for example, and many other compounds. And then in the first step, you get maybe 95% of ethanol. That's not a pure ethanol. There's maybe some water in that, maybe also some other alcohols like methanol or propanol, so with less or more carbon atoms than the two which you have in ethanol. And then there's a lot of more work to be done to come to the 100% of ethanol. So in chemical industry, totally you can always say making the reaction is an important step, but it is only one step. And then there's a lot of cleaning afterwards, and that's about distillation, there are extraction processes, there are many more, which you can have, membranes which might be involved. So this is always something one has to consider, that there is a lot of work to be done. Also afterwards, after you have, in principle, the final compound already produced. But that's more as a general thing. You should just see that there is a lot of things to do. That's a little bit the same. You see that we have different possibilities of microorganisms. We have this enzyme and the bacteria, also some fungi can be used. You have the yeast, you get the distillation columns, and then you get the energy at the end, the ethanol at the end. So, and then the question is, no, the question is not. There would be maybe a point what to do with this ethanol. But this maybe is something which is not so important for you, because here we will discuss about energy storage. But in principle, there is a lot of things to be done also with the ethanol then at the end. So that's the end of that presentation, I guess. And so we're coming to another one. And now I have to upload that again. There. Okay. Just a moment. Okay, then we go a step further and take this one. I hope that works. It's converting, that's great. Should be this one. This one. Okay, so I mentioned already enzymes. And so we have a little bit to look on catalysis, because in all these processes, what happens there in this conversion of chemicals, catalysis is also playing a role. That are only a few slides, so not so much. But it should give you some general aspects. Because the first is that we always have, if we have a chemical reaction, this reaction, as it is shown there, is not complete. Although you say if you have a nitrogen atom, N2, with a triple bond, which we had also seen already with this high amount of bond energy in this table, you saw that. We have hydrogen, and we can react that in a quite complicated but efficient process to ammonia. In this process, which you have, maybe I should give the name here, that's the so-called Haber-Bosch process. And this is important because that process leads to the formation, also a very important step. There is another one process coming in a further step. But that's important for getting fertilizers. And fertilizers you need for growing biomass, for example. For eating, but also, as we saw, for energy storage. So you have this reaction, nitrogen reacting with hydrogen to ammonia. And then you see there's one arrow in the direction forming ammonia. But in reality, there can also be the back reaction. So if you form an NH3 molecule under the same conditions, there is also a chance that this is reacting in a reverse direction. So it's a back reaction to form nitrogen and hydrogen again. The situation that you have at the start, a bunch of molecules, and then you get a so-called equilibrium. And the equilibrium means that you have not 100% of that what you started with, but also not 100% of that what your product will be, but somehow of that. And for example, here you see also in Germany the concentration above time. And you see if you run this reaction, you will have only a relatively small amount of ammonia at the end, and you still have a lot of nitrogen and hydrogen. So in principle, that's not a very effective reaction. And that's the reason that we have to speed up the reaction also a little bit. What will be then the need for having catalysis. But what you should also have in mind, at least a little bit, is that the energy amount, and we discussed about that, about the energies, the reactants and the products, you saw that if there's such a difference between the two, then you have an exothermic reaction, so heat is produced. But in most cases, the most favorable state is in between. So that one, what we then call the equilibrium state, that's the one which you have where the energy, as you see that here, is even lower. And nature, and I mentioned that also before, is always trying to get the lowest energy content possible. And so this equilibrium is then something which is formed. So to remind, or what you should keep in mind is that there's, in most cases, a reaction which is going in both directions. If you just have a reaction of where you change, so say, the position of the atoms in the molecules, or forming new molecules from that. This is not the case if you transfer electrons. So if you transfer electrons, in a reduction or an oxidation reaction, what we saw before, they will always go in one way, because then nature decides whether that should be an oxidation or a reduction reaction. And it's not going in the reverse way. But that maybe only as a side remark. And then we have seen this figure already, where we discussed about what is an exothermic reaction producing heat, or what is an endothermic where you always need to heat it. And we saw what the reason for that is. That's just a reminder. And now we have to go for catalysis. And catalysis means that you now have a compound, so to say, a helping compound, mainly the catalyst, which has no effect on the thermodynamics. So it has no effect how much energy is either needed or released at the end, but it has an effect on that what we called the activation energy. And the idea of a catalyst is to lower the activation energy. So what a catalyst is always do is lowering this activation energy for a process. And you may have a look on this cartoon, which is maybe a little bit misleading in some parts, but if you maybe are on a walk at the weekend, maybe not in Oldenburg because there will be no hills for which you can use, but maybe in the Alps or somewhere, and then you are here and you say, okay, in principle I'm thirsty and also hungry, so I want to find a restaurant, and some kilometers away there is some. And then you have to decide how to go there. Either on the easiest way, or maybe on the way where you want to have a nice look on the landscape. And so you can either go the way up on the hill, which is, or the mountain, which is there, or you can find a way which is easier and not climbing the mountain. And that's at least what also a catalyst is providing. The catalyst is providing you the second route. Or for a chemical reaction, it's providing the second route. So that means there might be a chance to come to the same place at the end, come to the same energy here at the end for the products, but to have it in an easier way with a less high energy barrier. And therefore, people have or still work a lot on catalysts. And you can see on this slide, there might be different reactions which you not have to consider too much. And there might be different catalysts, and you see there are different activation energies. And the lower the activation energy is for the reaction. So in this case, for the first reaction, the splitting of hydrogen iodide, it is platinum providing the lowest energy, lower than that what the catalyst gold is doing. If we want to split the nitrogen oxide, it's the other way around. There you see the lowest amount is now coming with gold. Problem with that is you always have to look for the reaction, what you want to catalyze, and then you have to find the best material for that. And there's unfortunately not a single rule where you say platinum is always the best catalyst. No, it isn't. It is for a lot of reactions a very good catalyst, but it is not for all. What you can see in this in this comparison. So that means that people in chemical industry, but also in fuel transformation and so on, they are always looking for catalysts. Because when we started this lecture today, we discussed about diesel and gasoline and how the different compounds are. The problem is they are both made from crude oil. And you have, on one hand, for the gasoline, you have to react the crude oil to something which has a lot of branched, short hydrocarbons. And for the diesel, you have to react the same crude oil to long carbon chains, which are favorable in the diesel. And all this is done by different catalysts. So people in the oil industry are looking for catalysts doing either the one reaction or going to the other. And so there are different catalysts developed for gasoline production, and there are different catalysts developed for diesel production. And that's always a lot of work to do to optimize the catalyst and to get a cheap catalyst, and with that, getting then also an efficient one, of course. And the final, not the final one, but maybe if you allow me some more minutes, the point is you have to look for activity, for selectivity, and for stability. And this figure here just shows we had already seen also carbon monoxide and hydrogen. That was Fischer-Tropsch reaction, what we followed. And we have seen that for that, we can, for example, go to gasoline, diesel, and wax. This was the other graph, which you had also seen today. But there might be also a lot of other reactions. That you can also form methanol, you can form higher alcohols and aldehydes, you can form simply carbon, which you don't want, and you can also form methane. And now the point is that a good catalyst has to really go only one way. So if you want to make Fischer-Tropsch, you want to have a catalyst which only follows this way. And that means you have a catalyst which has a high selectivity for exactly that reaction. And so selectivity is one of the main points for a good catalyst. And people are always looking to optimize also existing catalysts to get almost better with that. I guess that's where we stop now. I will tell you a little bit next week how catalysts might look like, and we will go back a little bit to enzymes, which I already mentioned today. And then we will go for hydrogen and other energy storage materials. Okay, thank you very much for today.
Now you're talking about we went back to the exothermal and endothermic reactions. Like, let's say we give activation energy and we break the bonds, and then the new products are formed, and let's say it's an exothermic reaction, and let's say the sum of the bonds energy of the bonds is like 5,000 kilojoules. Let's say we give 4,000 kilojoules and other side is 5,000, so we know it's exothermic. So the amount of energy set free is 5,000, 4,000.
No, the amount of energy set free is always that what you go from the exothermic reaction. So from the different You have here. This is the way, the amount of energy you get. Yeah. This energy, this activation is fully independent of it. But you can, of course, if you produce this energy, that will help you to overcome this barrier. If you continue the reaction. And at the starting of the reaction, you always have to bring this activation energy for that.
Okay. So now, okay, now I understood. The amount of energy set free here is 1,000, not 5,000 because, okay, that I understood. Now, when you use a catalyst, anyway, I mean, from what we learned in the first lecture, we need to break these bonds in the reactor. Okay. So if you're using less activation energy, then the other energy provided by the catalyst.
The point is that with the catalyst, you have the catalyst material also there, and that catalyst helps to split the bonds in the starting molecules. Because you get the reaction of these atoms then also with the catalyst. So they bind partly at least to the catalyst. And that leads to this lowering in the energy there. So you, with the help of the catalyst, energy.
But you also mentioned at the end of the reaction, catalyst is not changed.
No, the catalyst is not changed because at the end, if you go then to the product side, all the atoms which are maybe bound to the catalyst in degree, they are released.
Basically, catalyst is like reduces the activation energy plus. Yeah, actually, yeah. Reduces the activation.
That's what we do.
But anyway, like when you think of it in this way, like when you calculate the sum of all the bonds in the reactants, then it looks like okay, you need this much of energy, but actually you don't need that with the catalyst.
That's true. But the point is, that I said, that upper part here, that's only thermodynamics. So that's really the calculation of the energy, which I either need or not, or get. This is the kinetics, that's just some energy gain in between.
That's what the catalyst gives.
So at the end, so that's interesting this is interesting at the beginning of the reaction. This is more or less at the end of the reaction.
So there are like kind of two things to a reaction, like thermodynamic and kinetic. I think where the catalyst plays a role is kind of in kinetic.
Yeah, that's it. Okay.